Hey Emily, I'm going to try to walk you through this example 5 in section 4.4 of our book. Ultimately our goal is to take this function and factor it as much as we possibly can so that we can find its zeros. Well, this function is not easy to factor. It's not something that we can factor using any techniques that we've learned in this class prior to this chapter. The only way to factor this thing is to find zeros for this function one at a time and divide them out using either long division or synthetic division. So we need to start by finding one zero of this function. How do you do it? Well, it turns out there's a theorem. It's called the rational zeros theorem. And it says that if this function has rational zeros, rational meaning they can be written as a fraction. If this function has rational zeros, we can find them by first writing down all of the factors of the constant term in the function. And we call those factors p. And the factors of 4 or negative 4 are either plus or minus 1, plus or minus 2, and plus or minus 4. We take all of those numbers and we divide them by all of the factors of the leading coefficient, in this case 3, and we call all of those numbers q. That's plus or minus 1 and plus or minus 3 are the factors of 3. Now what this theorem says is that if we take all of these p values, every one of them, and divide them by every one of these q values, we're going to get a big list, and this is the list of all of the possible rational zeros of our function. Okay, so 1 divided by 1 is 1, and 1 divided by 3 is 1/3. 2 divided by 1 is 2. 2 divided by 3 is 2/3. 4 divided by 1 is 4. 4 divided by 3 is 4/3. So we've taken every one of our p values and we've divided every one of these by every one of our q values, and we get this big list. And there's a plus or minus on every one of these. So our theorem says that if this function has rational zeros, those rational zeros will be right here on this list. So the question is, which ones are actually zeros? Well, that's a little bit harder because we have a pretty big list to go through. So what you certainly could do is you could start with the very first one on your list and plug in, say, x equals 1 into the function and see if the function equals 0. And then if it doesn't, you go on to negative 1. Take negative 1 and plug it into the function and see if it equals 0. And you could go through your whole list until you find a 0 of that function. What the example decides to do is they decide to actually graph the function on their calculator and look at the graph and try to guess which one of these is actually a 0 of the function. So what the example does is they look at the graph and they look at it and they say, well, I'm guessing maybe x equals negative 1 is a 0. It looks like 1/3 could be a 0 as well, and it looks like maybe 2/3 could be a 0. Well, we're not sure which ones of those are zeros, if any of them, but at least it's a shorter list than this list of 12 possibilities up here. So again, you could take these numbers and plug them into the function and see which ones make the function equal 0, and that would be totally fine. However, the book uses a slightly different approach. What your book does is it sets up a synthetic division problem. Notice they took the coefficients from this polynomial up here and put them down here, and they're going to set up a synthetic division problem, and they're going to say, well, let's try our first guess here, x equals negative 1. One note here is, why is this 0 here? Well, there's a 0 here because, as it turns out, there's no x squared term in this polynomial, so there's a 0x squared term in there. You need that placeholder. Let's run through the synthetic division problem. When you do the synthetic division problem, you get a 0 remainder. And that 0 remainder means that x equals negative 1 is in fact a 0 of our original function. And that's great. That's what we were trying to find. We confirmed that x equals negative 1 is a 0 of our function. But what the synthetic division problem also does is it allows us to rewrite the function. Because what we just did with synthetic division was we factored out a factor of x plus 1. What we're left with, in this case, is 3x cubed minus 14x squared plus 14x minus 4. Where did I get these numbers? Well, these coefficients came from what was left in the synthetic division problem. Okay, so that's all well and good, but I still don't know how to factor what's left of this function. So we actually need to go through this process again. We need to find another 0 of this function and divide it out of, let's say, this function now with synthetic division. Now the book tries to divide out the 0 x equals 1/3. And when they do that with synthetic division, they don't get a 0 remainder here, so it actually doesn't work. So what I'm going to do is I'm going to move right along to the 0 x equals 2/3. I'm going to set up a synthetic division problem with the polynomial that we have remaining that we still want to factor here, and a 0 of 2/3. And I'm going to see what's going to happen. So I did the synthetic division with a 0 of 2/3 and this polynomial that remained, and we got a 0 remainder. So that's a really good thing again, because that tells us two things. It tells us, one, that 2/3 is in fact a 0 of this polynomial, and it also tells us how we could factor out that factor. Now looking back at our function, we had this factor x plus 1, and now we're taking what was left and we factored out an x minus 2/3. What remains of this polynomial now is 3x squared minus 12x plus 6. Again, I got those coefficients from what remained in the last line of the synthetic division. What your book points out at this point is that there's actually a factor of 3 that you can take out of each one of these terms, and eventually what they do is they take that 3 and they distribute it through that one set of parentheses. They chose that set of parentheses to clear the fractions on the 2/3. So now we've taken our original function, we've taken out two factors of it, we've completely factored it as far as we can go. We were left with the quadratic that cannot be factored. And the only way to find the zeros that correspond to that factor is by using the quadratic formula. Okay, basically I'm going to stop there because this video is getting kind of long. But this factor here is going to give you x equals -1 as a 0. This factor here gives you x equals 2/3 as a 0. And this factor, when you do the quadratic formula, is going to give you x is 2 plus root 2 and x is 2 minus root 2 right out of the quadratic formula. So you actually end up getting 1, 2, 3, 4 real zeros, 2 of which are considered to be rational zeros because they can be written as fractions. Okay, I hope this helped you out a little bit. I'll talk to you soon.